Newton's 3 laws of motion. In this lesson, we'll be taking a deep dive into Newton's first, second, and third law, including providing many applications as well as opportunities to check your understanding. Newton's laws of motion. The first law is the law of inertia. If the net force acting on an object is zero, that object maintains its state of rest or constant velocity. Number 2, an object accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the object's mass. And number 3, for every action force, there is a simultaneous reaction force equal in magnitude but opposite in direction. Now, as we go through the lesson, we're going to deep dive into each one of these 3 laws. But before we get started, we need to have a unit for force, and that's going to be the Newton. A Newton is composed of kilograms, meters, and seconds, so make sure you have these units in your equations while you're doing your problems. Newton's first law of motion, otherwise known as the law of inertia. Things want to keep doing what they're doing. Stationary objects don't want to move, whereas moving objects want to keep moving. To cause acceleration, the net force acting on an object cannot be zero. So if you have a block, and you're pushing it one way with 2 newtons of force, and someone else is pushing the other way with 2 newtons of force, the net force is going to equal to 0, and therefore acceleration is going to be 0. That doesn't mean that motion is 0. If it's already traveling at 10 meters per second, it's going to keep traveling at 10 meters per second in the direction that it's already moving, but it will not accelerate. Now, if this object is stationary to begin with, so if v is equal to 0, then v will continue to equal to 0 until there's a net force acting on that object. For instance, if we were to change this 2 newtons force to the left to 3 newtons force to the left, then we're going to start to see an acceleration that's not equal to 0. Instead, we're going to see an acceleration that is to the left. This law has several important implications. An external force is required to change the velocity of an object. So if an object is not moving, or if it's moving a particular way, you need a net force to change that velocity. For an object to change velocity, including changing from v equals 0, the F net must be greater than 0. Objects at rest remain at rest unless acted upon by an external F net greater than 0, and moving objects continue to move in a straight line at a constant speed unless acted upon by a net external force. So if you were to kick a soccer ball into the air, it wouldn't just keep going forever. It would follow a nice parabolic path and come down. And that's because it's being affected by gravity. So you have a net force of gravity acting downwards on the ball, causing it to come down. And you're also going to have air resistance. Now, air resistance is going to oppose motion. So if the ball in the first part is going up and to the right, air resistance is going to move down and to the left. As the ball's falling down and to the right, in the second part, air resistance is going to be moving up and to the left. It's going to oppose motion. So you're going to have many opposing forces acting on this object as it's flying through air on Earth. But if you were to kick that same soccer ball in outer space, that ball would keep going in the same direction at the same speed forever because there's nothing in space to slow it down. There's no air and there's no net gravity acting on that ball, assuming you're kicking it in a spot where gravity is negligible. So here's some examples. For a rocket to get off the ground, you need a significant force acting upwards, which is going to be the result of the propulsion of this fuel going down. When the object's in space, it'll keep flying in the same direction indefinitely because there's very little external force acting on the object. Now, we can cause acceleration by using booster rockets in outer space as well to increase the speed, but our speed will stay constant if nothing else is applied to it. Other applications of Newton's first law would be when a car slows down quickly, the people in the car tend to continue moving forward, possibly crashing their heads into the windshield if they're not wearing a seatbelt. The seatbelt prevents them from shooting forward through the windshield. It's going to provide an external force back on the person. So in the bottom picture on the right, you'll see that as the person accelerates forward, you'll see that as the person continues to move forward, the seatbelt is going to cause an external force acting to the left, keeping the person in their seat. Airbags act in a similar fashion to stop the person from hitting their head on the dashboard or steering wheel during a front-end collision. Both of these things act to reduce the inertia experienced by the passengers. So in the airbag situation, again, it's provide a force backwards on the person, but that force is going to be less, and it's going to be for a longer period of time as the head hits the airbag. Check your understanding. You exert a force of 45 newtons up on your backpack, causing it to move upwards with a constant velocity. Determine the force of gravity on the pack. Pause the video and answer this question. So in this case here, there's your backpack. You're going to have a force upwards on the backpack of 45 newtons, but the keywords here are constant velocity, meaning that velocity is going to be constant, which means that acceleration is going to equal to 0. For acceleration to be 0, we need to have the sum of our forces equaling 0. That means that the force down must equal the force up. So if you have a force up of 45 newtons with a constant velocity, you must have a force down of 45 newtons as well. So determine the force of gravity acting on the pack. The Fg is going to equal to 45 newtons down. Check your understanding. The traction system below stabilizes the broken tibia. That's the bottom part of your leg bone. What is the force of the tibia on the pulley? Neglect friction. So you're going to neglect friction in the pulley systems here, here, and here. Hint, a traction system is meant to create an F net equal to 0 so that the leg doesn't move. For the leg to heal, it needs to be stationary. So you need to have everything set up so that the leg does not move. So you need to have an equal force up as you do down, right as you have left. So they're all going to need to equal each other. So I'd like you to pause the video and answer this question. So let's draw a free body diagram. So that's the leg, the part of the leg that's attached to the pulley system. We're going to have a string that goes up like that at an angle of 57 degrees, and we're going to have a string that goes down at an angle of 32 degrees. Now the weight that's attached to the bottom pulley system is 1.84 kilograms. To find the force, we're going to find the force G is going to equal to 1.84 times 9.8, and that equals to 18.03 newtons. Now you need to have equal force down as you have up, so that the pulley system doesn't move. So that means the force up here must also equal to 18.03 newtons. So what we're going to do is we're going to say 18.03 newtons and 18.03 newtons. And that's all the main information that we need. We don't need the mass of the leg. We don't need anything like that. So what we're going to do is we're going to find the sum of our x's and the sum of our y's, and then we're going to find the net force from that. So we're going to say our y's are going to go up and down, and we're going to say our x's are both going to go to the right. We are going to say that right and up are both positive. So to find the sum of the y's, we're going to take 18.03 sine 57, and then we're going to subtract, because the next one's going down, 18.03 sine 32, and that equals to 5.57 newtons. For the sum of the x's, we're both going to the right, so they're both going to be positive. It's going to be 18.03 cos 57 plus 18.03 cos 32, and that equals to 25.1 newtons. So now all that's left is to draw our triangle. So I'm going to go right and up. My up was 5.57. My right, to make my vectors a little more accurate, I'm going to extend that. That's going to be 25.1. And then we're going to find the hypotenuse right there. And that's going to be the sum of the forces. And that's going to equal to the square root of 25.1 squared plus 5.57 squared. And that equals to 25.7 newtons. We also need an angle. So that's going to be our theta. Our theta is going to be equal to tan minus 1 opposite, which is 5.57 divided by 25.1. And that angle becomes 12.5 degrees. Now we're going to need to have two sig digs in our answer because that's what we're given. We're told an angles are 32 and 57. So our final answer is going to be 26 newtons right, 13 degrees up based on my drawing. But that's not the full answer. The question asks, what's the force of the tibia on the pulley? So I'm going to make a little bit more room, and I'm going to draw what we found. So we said right and up. So the force of the pulley on the tibia looks like this, 26 newtons, and it's going to go right 13 degrees up, 13 degrees. But the force of the tibia on the pulley is going to be exactly opposite. So it's going to look like that. It's still going to be 26 newtons, and it's going to be 13 degrees, but everything's going to be a little bit different. So if we say the sum of the forces of the tibia on the pulley is going to equal to 26 newtons left, 13 degrees down. And that's our final answer right there. Newton's second law of motion. An object accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the object's mass. So the acceleration is going to be equal to the force divided by the mass. So if I increase the force, I'm going to equally increase the acceleration. Now conversely, if I increase the mass, I'm going to decrease the acceleration because it's going to be harder to accelerate a greater mass. Now to keep acceleration constant, if I increase the mass, as if I'm pushing a larger body, I'm going to need to increase the force an equal amount to keep acceleration constant. Newton's second law demonstration. What I'd like you to do is pause the video and check out simulation number 5. While you're at the simulation, I want you to record the accelerations for the 50, 100, and 200 kilogram objects using a force of 1,000 newtons. Perform the calculations yourself using F equals ma for each mass. What can you conclude about how acceleration changes as mass changes? What kind of relationship exists? Check your understanding. The mass of a hot air balloon, including the passengers, is 9 times 10 to the 2 kilograms. The air inside the balloon creates a buoyant force, that's a force upwards, on the balloon of 9.9 times 10 to the 3 newtons up. Determine the vertical acceleration of the balloon. Hint, the answer is not 11 meters per second squared up. So what I'd like you to do is pause the video and answer this question. So when we draw our free body diagram, we're going to have a buoyant force upwards of 9.9 times 10 to the 3 newtons, and we know that the mass of the object is 9.0 times 10 to the 2 kilograms. That means we need to have a force of gravity down equaling to 9.0 times 10 to the 2 times 9.8. And that equals to 8820 newtons down. So if we say that up is positive, so our equation is F equals ma. Now we're only concerned about the forces in the y direction. So we're going to say the sum of the forces in the y direction is going to equal to mass times acceleration. And then we can simplify and say acceleration is going to equal to the sum of the forces in the y direction divided by the mass. So let's find out the sum of the forces in the y direction over here. So sum of the forces in the y are going to equal to the force up minus the force down. The force up we know is going to be 9,900, and we know the force down is going to be 8,820. So the sum of the forces in the y direction are going to equal to 1,080 newtons up. So we're going to plug that into our equation over here. So we're going to say A is going to equal to 1080 divided by the mass, which is 900. So that gives us an acceleration of 1.2 meters per second squared up. And that's our final answer. So the big thing that people get tripped up on this question is they forget this force down. because whenever we're doing our calculation for acceleration, we always need to find the net force. The net force is going to be the key, and that's going to take into account all opposing forces as well as the forces that are given. So make sure in your questions that you always remember to include all the forces acting on the object. Check your understanding. A net force of 58 newtons west is applied to a water polo ball of mass 0.45 kilograms. Calculate the ball's acceleration. So I'd like you to pause the video and answer this question. So our free body diagram is going to look like this. We're going to say that west is positive, and we're going to say that there's a force of 58 newtons west on this ball. We know the mass of the ball is 0.45 kilograms, and we're trying to find the acceleration. We know the acceleration is equal to the sum of the forces divided by the mass. The only force included in this question is the force going to the left, so it's going to be 58 divided by 0.45, and that gives us an acceleration of 128.9 meters per second squared west. We need to have 2 sig digs in our answer, so our final answer is going to be 1.3 times 10 to the 2 meters per second squared west. Check your understanding. In a test of its braking system under ideal road conditions, a car traveling initially at 26.9 meters per second south comes to a stop in 2.61 seconds. The mass of the car with the driver is 1.18 times 10 to the 3 kilograms. Calculate A, the car's acceleration, and B, the net force required to cause that acceleration. So I'd like you to pause the video and answer this question. So here's our free body diagram. We're going to say that south is positive, and we're going to say that initially the velocity is going to be 26.9 meters per second south. The time that it's going to stop is 2.61 seconds, and we know the mass of the car is going to be 1.18 times 10 to the 3 kilograms. What we're looking for in A is the acceleration. That's what we don't know. Now we're going to use one of our kinematic equations. Since it's stopping, we also know that Vf is going to equal to 0. So we're going to use the equation A is going to equal to Vf minus Vi over T. A is going to be 0 minus 26.9 divided by 2.61. And that's going to give us an acceleration of negative 10.31 meters per second squared, which is going to equal to 10.3 meters per second squared north. 3 sig digs, and that's what we need. So that's our answer for A. Now B says, what force is required? Force is going to equal to mass times acceleration. The mass we're told is 1.18 times 10 to the 3. The acceleration is going to be 10.3, and that's going to give us a force of 12,161.7 newtons. We need 3 sig digs. It's going to be 1.22 times 10 to the 4 newtons north. Remember, we need our direction for our forces, and since we're stopping, the direction of the force is going to equal to the direction of the acceleration, which were both north. Newton's third law of motion. For every action force, there's a simultaneous reaction force equal in magnitude but opposite in direction. In other words, for every action, there's an equal and opposite reaction. When a balloon is inflated and released, the air rushes out of the nozzle, causing the balloon to fly in the opposite direction. And I'm sure we've all done this at some point or another. If you fill up a balloon and then release it, if the balloon is pointed as if it's in this picture here, the air is going to flow to the left, and that's going to cause the balloon to go to the right, equal and opposite. So you're going to get a force left of the air being sent out of the balloon, and that's going to cause a motion of the balloon to the right, equal and opposite. Another application is that of rockets. So as the rocket pushes the fuel out of the back, the fuel pushes back on the rocket to move the rocket forward. This even occurs in space when there isn't any air to push against. So a big misconception people have is that when the rocket fuel comes out of the rocket, it's going to push against something like air, and that air therefore is going to push back on the rocket, causing it to go up. But that's not the case. Instead, what happens is that simply the act of pushing the rocket fuel out the back is going to cause the rocket to go in the opposite direction. And again, this is proved in outer space, where if you fire a rocket in outer space where there's no oxygen, it will still be propelled in the opposite direction. Rowing is another good example. As you push the water back, you go forward. So think about a rowboat, and here you are sitting in the rowboat. If you want to travel forward in this picture, you're going to have to push the water backwards. So you have to put your oar like this, and then you have to make it go like that. And as you do, you're going to push water this way, which is going to cause you to be propelled that way. Check your understanding. A contractor is pushing a stove across the kitchen floor with a constant velocity of 18 centimeters per second forward. The contractor is exerting a constant horizontal force of 85 newtons forward. The force of gravity on the stove is 447 newtons down. A. Determine the normal force, Fn, and the force of friction, Ff, acting on the stove. And B. Determine the total force applied by the floor on the stove. So I'd like you to pause the video and answer this question. So we're going to draw a free body diagram. We know we're going to have an Fg, we're going to have an Fn, and we're going to say that forward is positive, and we know we're going to have a velocity of 18 centimeters per second. And to produce that velocity, we have a force horizontally acting 85 newtons forward. We're told that Fg is 447 newtons, and we're asked to find Fn and the force of friction. Fn in this case, since the stove isn't going into the ground or out into the air, Fn is going to equal to Fg, which is going to equal to 447 newtons, but now it's going to be going up. Force of friction we can figure out since the velocity is constant. Constant velocity means that the force to the left is going to equal to the force to the right, because the sum of the forces is equal to 0. So the force of friction is going to equal to 85 newtons left. Now B is a little bit more tricky. Determine the total force applied by the floor on the stove. So what forces are being applied to the stove by the floor? We have the Fn and we have the force of friction. So what we're going to do is we're going to set up our triangle using just these two forces. We're going to have the force of friction going to the left. We're going to have the force normal going up. Force normal was 447 newtons. Force of friction was 85 newtons. And that's going to result in the net force of the floor on the stove, which is going to equal to the square root of 447 squared plus 85 squared, which equals to 455.0 newtons. We need to have an angle, so that theta is going to equal to tan minus 1, 447 divided by 85, which is equal to 79.2 degrees. So our final answer is going to be to 2 sig digs, so 4.6 times 10 to the 2 newtons. Now we're going to say backwards, 79 degrees up. Check your understanding. Sleds A and B are connected by a horizontal rope with A in front of B. Sled A is pulled forward by means of a horizontal rope with a tension of magnitude 29 newtons. The masses of A and B are 6.7 and 5.6 kilograms respectively. The magnitudes of friction on A and B are 9 and 8 newtons respectively. Calculate the magnitude of the acceleration of the two sled system. So I'd like you to pause the video and answer this question. So let's draw it out. We're told that A and B are connected by a rope with A in front and B behind. Sled A is pulled forward by means of a horizontal rope with a tension of 29 newtons. The masses of A and B are 6.7 and 5.6 kilograms respectively, and the magnitude of the friction on A and B are 9 newtons and 8 newtons respectively. Calculate the magnitude of the acceleration of the two sled system. So we know that acceleration is equal to the sum of the forces. In this case, we're just looking at the x because we know it's not flying into the air or going to the snow, so we're not concerned with the y. They're going to cancel each other out. So the acceleration is going to equal to the sum of the forces in the x direction divided by the mass. The sum of the forces in the x direction are going to equal to 29 minus the force of friction of 9 minus the other force of friction, which is 8, divided by the two masses put together, 5.6 plus 6.7. And we calculate that through, we get an acceleration of 0.98 meters per second squared forward. And that's the 2 sig digs which we need. Now it does just say magnitude, so our actual final answer is 0.98 meters per second squared, because magnitude just means the number involved. Check your understanding. At an indoor skating rink, children skate with their parents. Behind each child, a parent also on skates prepares to push horizontally to see who can push their child the farthest. In this competition, a certain mother has a mass of 61 kilograms and her daughter has a mass of 19 kilograms. Both skaters experience negligible friction. At the starting bell, the mother pushes the child with a constant applied force of magnitude 56 newtons for 0.83 seconds. Determine the magnitude of A, the daughter's acceleration, B, the mother's acceleration, and C, the maximum velocity of the daughter. So I'd like you to pause the video and answer this question. So we're going to need multiple free body diagrams. So for A, let's just focus on the daughter. So the daughter has a mass, we're told, of 19 kilograms. We're going to say that that weighs forward and is positive. We're told that she's pushed with a force of 56 newtons for 0.83 seconds. Now the 0.83 seconds isn't going to mean anything for the first two questions. We need to find her acceleration. Well, her acceleration is going to be the sum of the forces divided by mass. So plugging in our numbers, our acceleration equals the sum of the forces, which would be 56 over the mass of the daughter, which is 19. 56 divided by 19 is equal to 2.94 meters per second squared forward. Now we need to have 2 sig digs in our answer, so our final answer is going to be 2.9 meters per second squared forward. That's our acceleration. For B, we're asked the acceleration of the mother. So keeping in mind, when the mother pushes on the daughter forward, there's an equal and opposite reaction in the other direction. That's also 56 newtons. So now if we're taking a look at the mother, draw a different free body diagram. We have our force going the other way, 56 newtons. Her mass now is 61 kilograms, and we're going to do the same thing. We're going to say acceleration is equal to sum of the forces divided by the mass, which is going to be 56 newtons divided by 61 kilograms. 56 divided by 61 is 0.92 meters per second squared, and we would say backwards. So you can see the exact same force causing different amounts of acceleration because of the mass of the person. And then C, we're asked to find the maximum velocity. Essentially, that's VF. That's question mark. VI we know is 0. We know the acceleration of the daughter is 2.95 meters per second squared. We got to use that extra digit. And we know the time that she's pushed is 0.83 seconds. So we can use A equals to VF minus VI over T. We can rearrange and solve for VF. VF is equal to AT plus VI. VF is equal to 2.95 times 0.83. VI is 0, so we get a final velocity, a maximum velocity to 2 significant digits of 2.4 meters per second forward. And before we conclude the lesson, I want you to pause the video and watch number 9. Once you've done that, you'll have completed the lesson on Newton's laws of motion.